Let's talk about the adiabatic flame temperature next. So last time we talked about the first law applied to steady state combustion. And what we developed was that the first law could just simply be adapted by saying Q minus W is the sum of the products, the moles of each, times their enthalpy minus the reactants and the moles of each times their enthalpy. But the enthalpy this time became the heat of formation from the atomic simplest parts, plus the enthalpy change of that material to go from the standard state, 25 degrees C, to whatever your inlet or exit condition was. So if we want to talk about an adiabatic flame temperature, what we're going to be doing is assuming that there is no heat transfer, so Q is going to be 0. And there's no work in a fire, and so therefore we really are just going to be having the enthalpy change equal to 0. So this should give us the highest temperature that is available to us. Now we're going to want to look at this various ways. One is, what if we had exactly the correct amount of oxygen for complete combustion, which means that we would be operating with theoretical air, or if we have excess air. Now we've already looked at this once before using this diagram here. We know that as we have less air than required or more air than required, we had changes in how much fuel was left at the end, how much carbon monoxide would be formed, how much oxygen would be left at the end, but also something about the fire efficiency, which really is about what temperature am I able to obtain for this reaction. So what we want to do is we want to see if we can determine what the amount of the final burn temperature would be, or at least to get an upper estimate of this. So let's do this through an example. We're going to look at the adiabatic flame temperature for combustion of methane at 37 degrees C. Now, unfortunately, to do this problem, it really becomes trial and error if you use data tables, because you don't know the final temperature, and so you have to just keep trying temperatures until you get delta H equal to 0. So the alternative is to use equations, and recall that the integral of Cp dt is also equal to delta H, and we'll use that. So if we're going to do an equation that's a little bit complicated, it's easiest to do it in Excel. So let's switch to Excel. So let's look at methane. If I just simply do complete combustion, I have methane plus air, O2 plus 3.76 N2s is air, and it's going to make CO2, H2O, and N2. If I'm going for just complete combustion, I have no oxygen left. So I balance this by looking at my carbons, and I see I need to produce 1 CO2. I look at my hydrogens, and so I need 2 waters. And then I balance my oxygens to come up with how much air will come in. The exiting nitrogen is going to be the result of taking these 2 moles of O2 times 3.76 for the accompanying nitrogen. Now if I do 10% excess oxygen, then I would simply take this number here and multiply by 1.1. And it's not going to change the amount of CO2 or H2O formed, but I will have extra nitrogen coming in with that oxygen, and I'll have some leftover oxygen. In this case, what I have is an air to fuel ratio on a molar basis of 2.2 times my moles of air, which is oxygen and nitrogen, 4.76, divided by my 1 mole of the methane, giving me an air to fuel ratio of 10.5. Now, what we're trying to do today is come up with the temperature for combustion if Q is equal to 0. And our path for calculating delta H is a little bit on the strange side. We start with, I said 37 degrees this time, fuel and air coming in at that inlet temperature. I'm going to need to, in my mind, cool them to 25 degrees C. Okay, so they haven't changed substances, but they have just been cooled to 25 degrees C. This is necessary because this next step I only have data at 25 degrees C. So we're going to be using heats of formation, so I will break these down into their elemental components at 25 C. Then I will take those elemental components and reform them into the combustion products, but still at 25 degrees C. And then finally, I will be able to take these to combustion products. This is going to be my delta H for my feed materials. This is delta H for my combustion materials, my combustion products. These are heats of formation of the reactants, heats of formation of the products. So the data I'm going to be needing in this case is I'm going to need the enthalpy differences for the feed materials, methane, oxygen, and nitrogen. I'm going to need heats of formation of all of my substances, and I'm going to need enthalpy difference data for all of my combustion products. So if we go looking at the tables, what I found is that for methane, I can find heat of formation. CO2, H2O, no problem. Oxygen and nitrogen do not have a heat of formation. Well, the heat of formation is 0 because they are already elemental. Okay? So those are fine, but I need enthalpies at the feed temperature and the exit or 25 degrees C, that reference temperature. And I have that for all of the standard combustion product gases, but I don't for methane. I do not have a table for that. So we're sort of kind of stuck. I don't have the data I need here. And for all of the enthalpy at the exit temperature, I don't know what the temperature is, so I would have to do trial and error, looking up numbers, interpolating until I got it so that the correct combination worked for all of these. So the easiest thing to do is to use the integral of Cp dt. So the data for that, this is out of the back of the textbook, has coefficients A, B, C, D, and E. And if I were to integrate this, I have AT 1/2 BT squared, 1/3 CT cubed, 1/4 DT to the 4th, 1/5 ET to the 5th. And I'm going to evaluate this at the final temperature and subtract off at the initial temperature. So if I did that, then this is the information that I got for each of these components. The heats of formation out of the data table. The enthalpy at 298 using this gives me delta H for 310 of this, delta H at some guess of the flame temperature, and I can get delta H for each. Now the trick is I don't know what that flame temperature is, so let me reset it. I'll call it 1000. Okay, so if my flame temperature is 1000, I have it so it changes the temperatures on all of these all at one time, and it's going to calculate for me the temperature, or the enthalpy at this temperature, subtract off the enthalpy at 298. All right. Now I'm going to, of course, need to have the flows or the mole quantities of the inlet and the exit product. So I just took these from my balanced reaction. And so coming over to my energy balance, I'm just saying that the heats of formation plus the delta H for my feed and my products will be equal to each other. So I just multiplied number of moles times the enthalpy of formation plus number of moles times the enthalpy change to get to 310, or the product temperature for each one. So just looking at this, I took this plus this, this plus this, this, and added it to this and this, and this. Did that for each of my substances. Set it equal to the moles at the outlet times heat of formation and enthalpy at the flame temperature. Now I did this for a guessed value of flame temperature. I set an objective function where I wanted these two to be equal to each other, so I just simply subtracted. Then, you can use goal-seek, solver, whatever is easiest for you to use. So let's try it with goal-seek here, since that's the one that's automatically set up in Excel. I want to set this to a value of 0 by changing that. And if I say OK, it changes it. The number is now very close to 0, and the temperature, therefore, was 2498. Well, I just told it not to save that. That was silly. And you can do that. And you can do this. I set this up so you could do it for different excess oxygen. So at 10%, it was around 2500. If I change this to 30% excess oxygen, excuse me, let me get this set up so we can see both at the same time. There we go, 30% excess oxygen. Selected goal seek from the what if analysis on the data tab. So I'm setting this cell to a value of 0 by changing this cell. Okay. And so the temperature went down. And the more extra oxygen I keep adding, the temperature will continue to decrease. It has to decrease because what I've done is I've added extra materials, cold inerts, things that are not taking part in the reaction. And I'm having to heat these up, so I'm wasting some of the energy on heating up the carrier gases. So you can see a relationship between why you may wish to add excess oxygen because it allows the molecules to find each other and react, but maybe not too much because it lowers the possible temperature of our flame. So that concludes this video on adiabatic flame temperature.